Hello everyone, I'm really glad to be here. I'm G.Lombardi. I work in ARGO Vision. We do computer vision. We work in many fields. Now we are working almost mainly in the pharma field. So we process images to do checks or quality checks on the production, almost. I will speak today not so much about computer vision, not so much about embedded devices, so why the title? Mainly about software architectures constrained by the fact that we work on embedded devices and we must manage computer vision algorithms and pictures. And pictures are heavy to move across the network. Maybe the network is not available at all. So we want to have something that is fast enough for the task on a constrained environment. So that's the point of today. So what means fast enough? Means that we wish to have the right latency or the right throughput depending on the application. And we must use just local resources. So we will not want to scale in the sense of adding hardware to getting something faster. Obviously, these kind of applications are CPU and GPU, VPU, and whatever intensive. And we will consider them as a composition of building blocks because that's it. Also, if we write new algorithms, generally we develop these building blocks and then we have the issue of composing them, also if they are custom. We will take a look to a toy problem, a really easy problem that is having a video stream from a camera, detecting faces, and on those faces detecting facial landmarks. Okay, that's something we used. We also developed from the algorithm point of view, so a face detector and landmark detector, but that's not the point for today. We have the building blocks already made by someone else, and we just want to compose them, identify the best composition depending on our task. So the problem is made up of components that are interdependent and that may have different priorities. Maybe we want to have landmarks if possible. When not possible, we want to have just the face detections as an example, and with different time constraints. Okay, so how to do that? Just one point, you will find the presentation, the demo code on GitHub. I will not show you all the code because I think it's useless, but you can browse it, or if you want for change or request, do whatever you want. So for us, the problem is solved this way. We have in Python our building blocks, and we don't care about their implementation that is native and will be, let me say, as fast as possible. That's generally never true, but let's say we cannot get something better from this stuff. Okay, so Python here for us is an orchestrator of low-level algorithms, low-level in the sense of low level after the interpreter, okay, under the interpreter. There are many architectures we also use. Maybe all of those I listed, they are not all the architecture we want to use. And we will speak today about pipes and filters. All of you know about pipes and filters for sure, but I wish to check what's good, what's bad, what are the choices related to pipes and filters. Okay, so just to say, monolithic application, let's write code as we need, just an unstructured set of operations. Let me show you the code. No, yes, just the code, not the demo. But yes, we will run the demo too. You have all You have all this demo if you want, but we will not check all of them. Okay, this is the example of an unstructured code that is just write your operations, take the outputs, use the outputs where there are dependencies, and so on. Okay, this is pretty good. It's bad from my point of view, but it's pretty good because it's sequential. It's really simple. It's not so bad from the performance point of view because there is not much overhead. If you add stuff to orchestrate things, you add overhead. Here, I take the result of the gray image here, I put it where it is needed, and there is almost zero overhead. Okay, so why changing this kind of architecture, if you can say that? Because it can be faster, because it's not configurable, because we like to build blocks and compose them, maybe another motivation, okay? Let's not read this stuff. These are just a bunch of questions we want to answer. We'll try to do that. So pipes and filters is made up of pipes and filters. In this drawing, you can see the filters as blocks and the pipes as connections. Obviously, data flow through pipes from one filter to another one. Okay. So the main block, from my point of view, is not the filter, it's the pipe. The name is not filters and pipe, but pipe and filters. And the pipes are those pieces that connect things. And they can be as easy as a function call, so direct connection, or they can manage communication across threads. Yes, we can also have a direct call to stuff that communicates between threads, but at the end, we want something to synchronize them. Or across machines, across clusters, across the network, no. Avoid, in this kind of architectures, the network for two reasons. The first one, maybe we do not have the possibility to work with the network. In the farmer field, this is something normal. You cannot connect your system to something that is far from the line of production. And because the latency you have communicating on the network may be low, but has a large variance, sometimes maybe unreliable, and you can get spikes of latency. So you don't want that. Transparently, obviously, it's not another kind of communication, but it's the idea to abstract, as usual, the communication, so that something else manages what kind of communication you must use on a single pipe. What you can see here is obviously one kind of pipe, one implementation. It's a queue. In general, if you have threads, you want to make them communicate, and they must communicate through queues. There are many kinds of queues. You can implement your own if you want, but it's not a good idea to do that. In Python, you have lists. Do not use lists, very, very bad. It may be good from the performance point of view only if you use the list like a circular buffer, but don't reinvent the wheel. Okay, so use what is already done for that. You have the queue or the deck, and the deck is the best one. Let's try with the first demo, and obviously it will not work, but let's try. Yes, maybe that's not so important to see that I'm saying simply run the script. The script is this one, QBench. Okay, oops, thanks. What it does is just to taking an implementation of a queue, executing a certain number of iterations of message passing of two threads through that queue. And we are trying to use these implementations, very simple implementation by means of a list. You can quickly pop from lists, but that's not so quick to insert at the very beginning of the list. So this is very slow. The queue and the deck are already have the operations we need. Okay, so let's try with some number of elements. And for the list, poor list, we cannot run all the tests because it's too slow. let's try just to see a result. If you want, I can make, but I think it's not so interesting to see numbers. It's better to see the graph at the end. Can you see? Can you see that the list is super, super slow? The queue is good, but if you want to avoid overhead almost, the deck is very, very close to zero overhead. It's not zero, but it's very, very close. So this is the deck, how it performs. The queue, it's bad with respect to the deck, but it's working, the list spikes. This is a log diagram. If you look at it without a log, you see that these two are linear, and this is not, okay? But every point will be pushed over there behind the origin, so the graph was bad. Okay, so let's go back to, okay, so use DEX for sure. Given that we have now some pipes, we must identify the right way to connect our filters with those pipes. So we have many topologies we can choose from. Wow.
I have a question.
Better. Yes?
Before we move forward, you said we are going to manage transparently. What does that actually mean? Like the pipelines are managing or the filters are managing the flow?
We will speak about that in a few minutes. Yes. Let's speak about the topology now, and then we will speak about the flow. So pipeline generally is associated with a pipeline pattern that requires to have a chain, simply a chain. What's good about the chain? What's bad about the chain? We are limited, obviously. But what's good about the chain, it's really simple to manage from many points of view. DEC and queue are multi-producer, multi-consumer queues. But here, eventually, we need just the single producer, single consumer queue. And there are implementations that are also lockless, so it can be really, really fast. But no, let me go back. Also here, we must ask ourselves some questions about the task. So this is an architecture that can do two things. We will speak about multiprocessing later, but this can do at least two things. It can process every single token, message. Let's call them images, but because images are what we are processing. Every single image incoming, but we can also put queues in the middle that instead of being blocking queues are discarding queues like leaky buckets. Okay, so we can decide if our application must process everything or our application needs to be real time, eventually discarding some processing. And we face both the situations, and they are completely different. Obviously, we can use trees, so we can add a new building block that is some fork, maybe a fork, maybe in the sense that we can here decide to distribute the frames between the target filters, or we can duplicate those frames to do different things. Okay, duplicate not in the sense of cloning, but in the sense of sending that frame to all the listeners. Obviously, I said listeners because one way to implement this is to using the classic pub/sub, the pub/sub pattern or observer or whatever you want. Okay, we can do also the other thing here, that is joining. Joining means that we can here do two things again. We can let frames flow and pass through E without syncing, or syncing in pair. Consider as an example an application where we are working with two cameras working together, and we want to do comparison between these two images to get a depth map. To do that, we want to work with both frames. We can calculate this disparity map here only with the two frames together. So in that case, we need to synchronize. Okay. Here we cannot use this kind of queue that is really simple. Also, the single producer multi-consumer queue can be implemented lockless. It's not so easy, but it is possible. I don't know about multi-producer, multi-consumer queues lockless, but maybe they exist. I don't know. The last possibility, obviously, is to have something that is not a DAG, but is an arbitrary, fully connected, at least, graph. Here we have feedback loops. How can we manage feedback loops? Obviously, here we cannot synchronize. We can just get feedback, and we have many algorithms with that feedback loop. In general, this feedback allows to collect statistics, to tune the execution of the algorithms. Okay, I mentioned some kind of, let me say, patterns, messaging patterns. There is an interesting paper speaking about this kind of stream algebra, as they describe it, name it. And it's quite interesting. I found a lot of patterns I used without knowing that they have been described in an algebra. They distinguish two levels. First level of algebra, where they have the single messaging, and the second level algebra, where they have composition of the first level pattern. So it's interesting if you want to take a look. At the end, there is a bibliography, so you will be able to find the titles of the papers. Okay. Last but not least, obviously, pipes and filters. There's also the filters. What are filters? They can be quite complex things, but at least they must be callables. We must pass data through something that can be as easy as a function or something more complicated. The interesting points are that a filter processes something. It's described also by ports that we can call, if you want, in and output arguments, but the name is port. They can be typed if you want to check that everything is okay when you assemble the network, the graph, and you must start it by the care of checking. You must somehow, we will see in the code, you must somehow manage the life cycle of these filters. That is, every piece in the graph must initialize itself. As an example, the face detector must load the data from a model and initialize itself, okay, or the camera must be switched on and so on. So, and at the end, they must be gracefully shut down. So the management of the life cycle is not so easy, depending on the pattern we use. And then these pieces must be parameterized and also assembled. In general, inversion of control gives us the possibility to create pieces that are building blocks, simple building blocks, and assemble them to solve different problems on different deployments. Okay. One point that is interesting, as usual, is that stateless is better than stateful, and stateful, in this kind of application, stateful must give some guarantees. As an example, if we collect frames to do something, as an example, clustering, we want to cluster the pictures that arrive. In general, we use the clustering to prevent processing things that are very, very close to each other, or collect data sets to do training of neural networks, reducing the correlation between pictures. These kind of operations must guarantee that the maximum number of pictures retained is bound. Otherwise, our processing can get spikes of memory and drops down. Okay. Flow management, you asked about that. Flow management means we need something that makes the pumping data around. Let's say also here we have different possibilities. The obvious one, the easier one, is pushing. So there is a source. The source in our case may be the camera. Okay, the camera gathers data from nothing. In our case, from the device drivers or whatever, and pushes in the graph the frames. This means that we can run it simply by taking the source and pushing the requirement for a start. Here we are giving the source a frame to process. What is a frame in this case? A frame is a container with the image, maybe, but in general with data. Okay, the data are collected during the processing in the graph. You can see this pattern called also whiteboard. We threw a whiteboard inside the graph, and the whiteboard is written by the filters so that every filter can find the data it needs written by the previous filters. Okay. One way to implement this is by means of a simple abstraction. In this case, we're using a class. But in the examples, I inserted also a functional style code because obviously you can use whatever you want. Okay, so the pump here is the runner that requires to the source to do something. Obviously, we can do the opposite. We can pull, so ask to the graph, okay, give me a new data, a new frame, and the call falls back to the source. One way to get this in Python is using generators. That's pretty easy. So the runner pulls from the last steps inside to the source. The source produces the frame, and the frame then is moved up to the runner. In this case, the runner must throw away the result because our task was just to traverse the graph, and there is one step at the end that shows the video, so we need nothing. Okay, what is the problem of generators in this case? That we can just implement easily the pipeline. Maybe we can have a good DAG, but with complexities, we cannot get something general. Okay. Generally, neither pull nor push are pure. Somehow there is always a pull-push case. So there is something in the middle that pulls data from one side, maybe the source from the camera, and pushes the result, the data to the rest of the graph. For sure, this happens always if you have a queue between graphs. So you have at the end of the thread, let me say, boundary, a tool that must push into the queue. So if your architecture is pull, you must pull from the graph and push into the queue, and vice versa on the other side. Okay. Another possibility is to use events. You can use events both in the push manner and pull manner. What I want to say here is that the event bus can be a component that allows you to decouple the filters, decouple the presence of queues, decouple in general the messaging issues. And you can configure the event bus to connect things. Okay, this is another solution. Obviously, this gives you flexibility. In general, you lose in speed depending on the event bus you use. The idea here in the event bus, but in general, is to have the third view that is not from the push side or the pull side, but from, let me say, the top. So something external can move things into the graph. This is the case of vector systems as an example. Okay, there are no, not few, there are a lot of frameworks for doing this in Python. I implemented an example with PyCA, that is a simul porting of akka in Python. It's not fully featured, but I tried it just to give you an example. Two of the most known actor systems are Despian And Oscar is really interesting. Is something that today is very good for the field of deep learning for sure, because it's a device aware. It allows to move the processing on the devices having the needed hardware, such as an example, GPU. Okay, maybe we want to move the processing, so we move an actor where the CPU is present and free, and it's something Oscar can do. Okay, if you never read this book, it's interesting because shows you vector model. Okay, it's a tool, but in general, the messaging patterns that are similar to object-oriented patterns, but completely different because they are oriented to messaging between, in that case, actors, but in general, maybe between microservices or something else. Okay, in this case, the filter is an actor. The actor can receive messages, dispatch messages, and send messages to other actors. So we can receive the frame, we can process it, and send the results to the target requiring for this information. It's not, in my opinion, the best architecture to use, because you need to connect the actors, and you wish to have closer control on the queues. And here the mailbox, here the queue is a mailbox that receives messages to be processed, is something that it's not always easy to change, okay, to customize. There is another interesting family, always as an external flowing system, that is the timely data flow framework. Timely data flow inserts time in messaging. This means that we can have, as an example, a graph that is that has cycles, okay, and we can process data because we receive them with a generation timestamp. Maybe just a timestamp, the idea. But in many implementations, like the Naiad from Microsoft and timely data flow in Rust, this is just a number, an integer number. Okay. So in this case, you have data that flows in generations through the graph, and you can receive different, in one filter, you can receive data from different generations, and you can reconcile the data knowing which generation they are. There is a good framework that is Bytewax in Python that wraps timely data flow from Rust. And if you don't know it, take a look, it's interesting. It's another point of view, okay? It's generally used to build up things like updating results architectures, like the Lambda architecture, okay? Obviously, it can run in one process without the need for the network, as we said, so on. Okay, let's talk about distribution in threading. Have I got time? So, if the algorithms have insufficient parallelization, what does this mean? Generally, many computer vision algorithms are inherently parallel and use all the resources available. So maybe we run a face detector, in OpenCV, and we can take a look to the CPU, and it is using all the CPUs because the parallelization is under the level of native code. Okay, maybe that's not enough. Maybe the parallelization exists but on the GPU, and we want to do something else on the CPU while the neural network is evaluated, and so on. Let's take a look of what can changing the architecture. If the architecture is sequential, obviously we have the latency, that is the composition of the time of our algorithms, and we are not parallelizing at all. So our throughput is, let me say, the lower we can have in this case. Instead, using pipes, we can have parallel steps, but only steps that are not the same one, because we need to receive the data from the previous step to process them. Okay, so we gain something. We can gain more if you allow to have the same algorithm run in parallel too, and this can happen with asynchronous architectures like the async IO in our case. Okay, in general, if we use the oh my gosh, I will say it later. I don't remember the name. Very sorry. Yes, the event loop. The original pattern name was later. It's the same pattern. It has many names. I will remember. Maybe there is written in some slide. Okay, so threading. What we can do? We can have different level of where the threading is placed, where the parallelism or concurrency, depending, is placed. Maybe at the filter level, as we said, face detector in OpenCV is parallel. It's already working with many threads. We can have, obviously, one whole graph per thread. So maybe we have many threads working, I don't know, with many cameras, and each one can be parallel. Or else we can have a graph made up of subgraphs, and those subgraphs are threads. Okay. If this is not enough, in general, maybe you must revise your problem or your hardware if we cannot use other kind of processing devices. Okay. Let's see. The GIL. Okay, this is very bad for performances. We want to parallelize, and there is a GIL that makes our threads not really parallel, concurrent, but not parallel. What can we do? Nothing needed, because there is an API, obviously, to release the GIL. That is this one. Okay, there is a macro used in CPy. This is CPython as an example, the most used implementation of Python. What? Okay, the most used implementation of Python. There is a couple of macros in C that allows to disable and re-enable the GIL. The opposite of a critical section. So the critical section is outside, and inside there is the code that is unsafe. And NumPy, SciPy, OpenCV, and many other have algorithms that generally release the GIL. So we are here in our application, we have threads. These threads are not really parallel, but if we use operators that are from NumPy, OpenCV, and they are parallel, and they release the GIL, not all operators release the GIL, but many, most of. The tasks in this case are really parallel. So we can exploit the hardware anyway. And if this is not enough, wait for Python 3.13, because the Python enhancement proposal 703 is accepted and says that the GIL will be optional. Okay, we will be able to compile Python without the GIL. Okay, so the GIL is not an issue. We can have blocks that are parallel. What is another issue we will face? The fact that these threads can be unbalanced. So we can have threads that are faster to work because the algorithms are simpler, and some threads that are the real bottlenecks of our pipeline. In this paper, T-Time proposes many things, and one of those is to adaptively change the topology of our graph, combining those threads, those filters, let me say, that are too fast, or splitting those that are too slow, or balancing the load, replicating some filters. Okay. Okay, this is one possibility. We obviously can do this offline, designing our algorithm. The proposal there was to do that adaptively. Okay, I never done that adaptively, but maybe something we will try. ePipes is another interesting paper that says simply get the best from the fact that you can use simple connections in the same thread. So if we have subgraphs that use simple connections such as simple function calls as an example, we can have the best in the thread. And if we use the pipeline as topology that is linear and use single producer, single consumer queues in the middle, we will have the best we can from both. Okay. I can add that these threads can, instead of using communication through calls, can use async IO. This allows both IO operations to be not blocking, obviously, but also encapsulating them in threads to have the operations that work more like this than that. Okay. So I have an example for this. I will show you in a few seconds. Okay. What kind of messages do we want to move along our graph? Let me say we can, we saw two things at least. We can simply move exactly what we need. So we can have our filters that have the structure of our functions, let me say, with the inputs they need and the outputs they can produce, and we can connect them. How many minutes have I got? 10? 5? 2 years? 5, okay. So this demo, you will try it by yourself. And another possibility is to use generally the whiteboard. So you have one message born together with the source, and this message is passed and the data are collected. This kind of solution is obviously easier to use than the complex connections related to every single need of the filters on each other, but be aware of memory usage. So it's tricky from the point of view of memory usage. Okay. Sorry, I have no time. I can show you this example, just this one. So subgraphs. So consider to have something like this. Here we have one graph with, let's start from here, with a source, producing data, processing the image, producing the gray level image, producing faces, and I randomly split. In this case, it's randomly the first graph here. I need filters that interact with queues. So here there is a queue, the Q1. I'm putting data inside that one, and I'm gathering from the same queue in another graph, and I'm continuing the process. And here I'm connecting it back. So in this case, I have a loop in my graph, okay? And the other part is working with the display. In this case, I made this not just to show it to you, but because I need to have this running on the main thread and the source and the display in OpenCV working on the same thread. Not a random thread, but the main thread. So I'm ensuring there is a main thread working there. Okay, I have no time to show you the implementation of this thing, but it's async IO based. So it is exactly this case, and I want to try to run it for some reason, and you will see which one. If it runs, okay, it's running. And can you say what's going on? What's going on here? We relaxed one requirement. The requirement we relaxed is that using async IO, here we are not granted about the sequentiality of the frames. So if you want to maximize the throughput, it's the right choice. Obviously, if you need to have the the data processed in the right sequence they arrive, you cannot use this kind of result of architecture unless you have something that sorts your results at a certain point, but that's breaking the requirement to have bounded number of frames in the state of one filter. So in general, it's better not to choose this one. Okay. Okay, assembling means shortening the explanation of having a configuration file, using a system that allows us to do inversion of control or dependency injection as you want to say. We use Hydra for that. There are many other tools. Another possibility is to have auto wiring. That is something that you can see in Spring as an example, but in general, it's not so difficult to implement. So you can have these filters with the ports tagged, and you can automatically identify the connections using reflection. Okay. Okay. In general, takeaway. The takeaway is that architectures managing explicitly the processing graph are very useful because they allow us to configure them, to easily manage the concurrency, easily manage the bolts of our architecture. This is one picture from the T-time framework, and I here represented both the structure of the graph and its execution as a set of stages described in a configuration made up of input and output ports connected by pipes and traversed by a traverser during the execution managed by a scheduler. So as you can see, it's super clean. Obviously, pipes can be distributed, synchronized. In their case, the distribution is something admitted. In our case, generally, it's not. Okay. So it's 21:00.